Hey everybody, we're going to take a look at assignment 34, I believe it is. Let's just confirm that. This is our review. It's not a review back then, but it's a review. It's in-class review. Worksheet. Okay, and I'm going to do the exciting thing of not actually printing it out. Um, so you're going to have to look at it too when you go to do this. So I'm just going to say number one, function graph below, find the limit as x approaches 4 from the negative side of phi, and 4 from the negative side is infinity. And the limit, let's go a, b, the limit as x heads to 4 from the positive side of phi is also heading towards infinity. C, the limit as x approaches 4 of phi. Well, that's a really interesting question. Because in section 2.1, we would say infinity is not a number, and so this limit doesn't exist. In section 2.2, where we talk about limits involving infinity, we would be able to say that. Okay. D. F of 4. Well, that does not exist because there's this big old vertical asymptotic form. And then we've got E, which is the limit as x approaches negative infinity of phi. Well, that appears to be headed to, I actually want to say that's headed to 0. If you put -1 based on that picture, I probably wouldn't mark it wrong because I didn't give you a function to work with on your own. I just gave you that picture. But I think according to that picture, my horizontal asymptote on the left side is 0, whereas f, the limit as x heads to positive infinity on phi, I think that's heading to -1 for sure. Okay, that was question 1. How about question 2? Question 2 says, consider the function f below. For what values of x does the limit not exist? Well, so I think the limit does not exist at x equals -6 because I have that infinite discontinuity. But you might say it does exist here, because this is me thinking about 2.1. But if you said limit as x approaches -6 from the positive side equals the limit as x approaches -6 from the negative side of this function, and both of those are equal to infinity, I could see you making an argument for that this limit exists at this point. But yeah, I'm saying that's a point of discontinuity there. So yeah, maybe you're right. Okay, what about at -3? Well, at -3, I see that the limit as x approaches -3 from the negative side does equal the limit as x approaches -3 from the positive side. So that limit exists. The point doesn't exist, or the point exists but somewhere other than where I expect it to be. So yes, a point of discontinuity there, but no, the limit exists. I guess really then my only for sure place where I would say the limit does not exist is at x equal to 3. The limit as x approaches 3 of f of x does not exist because the limit as x approaches 3 from the negative side does not equal the limit as x approaches 3 from the positive side. Okay, please be in the habit of writing justifications. All right, the next 8 problems are find points of discontinuity and state the type. Well, 5 is a linear equation. Linear equations have no points of discontinuity, so no points of discontinuity. Okay, 6. Oh, no, that was 3. 3, 4. F of x equals x over x squared plus 1. That's a rational function. And we remember that it has an x-intercept at 0, it has no vertical asymptotes, it has a horizontal asymptote at 0. And so our graph looks something like that. See any points of discontinuity? No, me neither. No points of discontinuity. 5. Maybe we'll find some here. 5 says f of x equals x over x squared minus 1. Aha! This has infinite discontinuities at x equals 1 and x equals negative 1. Those are our vertical asymptotes. Vertical asymptote is an infinite discontinuity. All right, 6. 6 says f of x is x minus 4 for x squared minus 16, which is x minus 4, x minus 4, x plus 4. Sure glad we did all that factoring over the last couple of years. And so what do I see? I see a whole, which is a removable discontinuity at x equals 4, and another vertical asymptote. I see an infinite discontinuity at x equals negative 4. Ta-da! Done with 6. 7. Okay, so 7. f of x equals x over absolute x. So this is the one with the jump discontinuity. Remember this graph? As I plug in positive, like 5, 5 over absolute 5 is 1. 6 over absolute 6 is 1. So we're always 1 over here. But if we go in the other direction, if we put in negative 3 and negative 3, we have negative 3 over the absolute value of negative 3, which is 3. Negative 3 divided by 3 is negative 1. So here, I definitely see a discontinuity. And it's true that, on one hand, I want to say there's, because f of 0 doesn't exist, that's the reason for my discontinuity. And I'm tempted to say that this is a removable discontinuity. However, if I plugged in the hole here, would the function now be continuous? No. And if I plugged in the hole here, the function still wouldn't be continuous. So I think what I have to say is, and the limit as x approaches 0 from the positive side does not equal the limit as x approaches 0 from the negative side. It's the jump discontinuity, I think, that's maybe even more important. So even if you just put this, I'd probably say that's sufficient. Okay, 8. 8 says f of x equals sine of x squared minus 2. Well, this is theorem 7. Remember, f of x equals g of h of x. And theorem 7 said if h is continuous and g is continuous for all the outputs of h, then g of h equals f is continuous. So let's think about this. Is that continuous? X squared minus 2, I can plug any number I want into that, and I'm going to be good to go. Now, this is going to poop out some numbers. So when we think about the y values go from negative 2 to infinity. Well, so g, we want to know if g is continuous from negative 2 to infinity. Well, g is a sine graph. And sine is continuous everywhere. I can plug any number I want in. Certainly I can plug in numbers from -2 out to infinity, and this sine graph will just vibrate between -1 and 1. So I don't think there are any points of discontinuity in that one. Cotangent. Why, I'm just gonna be sure about it because, smart people ask questions. So we've got sine of x squared minus 2. Close parentheses. Let's take a look at the standard viewing window. Yeah, it's almost an oscillating discontinuity, but it in fact isn't. If I go over to my table and I plug in a 0, I get a number. Yeah, no error there. So where are we now? 9. 9 is y equals cotangent x. And so let's think about the graph of cotangent. It has vertical asymptotes at 0, pi, negative pi. And it looks like this. And so, wow, cotangent is going to have a lot of discontinuities. Well, I'm going to describe all of them and say x equals 0 plus or minus pi n are where the vertical asymptotes are for cotangent. Therefore, therefore, at x equals 0 plus or minus pi n are infinite discontinuities. Okay, please write sentences. And the last one we have on this front side is f of x equals sine x over x. Well, that's our dear friend. We know that the limit as x approaches 0 of sine x over x equals 1, but at 0, f of 1 does not exist. So if we look at this graphically, this kind of situation. So what kind of point of discontinuity is this? This is removable. It's a hole. There's a hole at x equals 0. Okay, let's flip on to the back. Find the limit of each without a calculator. Find the limit of each without a calculator. Well, let's take a look and see if we can find the limit of each without a calculator. 11. The limit as x approaches 1 from the positive side of x to the 4th minus 1 over x minus 1. Well, I see a difference of squares here, so I can treat this as the limit as x approaches 1 from the positive side of x squared minus 1, x squared plus 1 over x minus 1. And the limit as x approaches 1 from the positive of this, I see another difference of squares, x minus 1, x plus 1, x squared plus 1 over x minus 1. So these will cancel. So there's a hole at x minus 1, not a vertical asymptote. And if I now plug in a 1 for my x's, 1 plus 1 is 2, 1 plus 1 is 2, I get 4. 12? 12. The limit as x approaches 2 of x squared minus 4x plus 4 over x squared plus x minus 6. It's going to be the limit as x approaches 2 of x minus 2 times x minus 2 over x minus 2 x plus 3. So these cancel, and I'm left with this stuff. And I'm supposed to plug in a 2 for all the x's. 2 minus 2 is 0. 2 plus 3 is 5. I've got 0 over 5, which is 0. So number 12 is 0. How about 13? 13 says the limit as x approaches 3 from the positive side x over x minus 3. Well, this does have a vertical asymptote at x equals 3. It has a horizontal asymptote at x equals 1. If I plug a 0 in, I get 0. So my graph looks like this. And if I test 4, 4 over 4 minus 3 is 1, so I'm up here. So the limit as x heads to 3 from the positive side, that's infinity. That was 13. How about 14? Oh, what if we approach from the negative side, it says. Well, let's draw that graph again. We had horizontal asymptote, we up this way, we would come down this way, and so the limit as x equals 3 from the negative side of x over x minus 3 is negative infinity. And that's 14. 15 says the limit as x approaches 3 of x over x minus 3. Yeah, that limit doesn't exist because one end's going up there and one end's going down there, and we are not approaching the same thing from both sides. 16 says the limit as x approaches 0 from the positive side of x over absolute x. Well, we just graphed this. Come on, you know that that looks like this. So what's the limit of this function as x heads to 0 from the positive side? 1. Okay, 17. What happens when I approach 0 from the negative side? Well, as I approach from the negative side, I'm writing along negative 1. And 18 says the limit as x approaches 0. Well, because these limits aren't the same, I'm going to say the limit as x approaches 0 of x over absolute x does not exist because the limit as x approaches 0 from the positive side does not equal the limit as x approaches 0 from the negative side of x over absolute x. All right, that was number 18. What about 19? 19 says the limit as x approaches 3 from the negative of 1 over x minus 3 in absolute values. Ooh, and without a calculator. Damn. Okay. Yeah, what the hell does that look like? Well, let's graph the original function without the absolute values. So it would look like this. 3, horizontal asymptote at 0, negative 1/3. And so I'd have this, and I'd have this. But if I put this in absolute value, I can't get any negative numbers out. So this is going to become this. So the limit as x approaches 3 from the negative side, I'm headed up towards infinity. Okay, I do, since I started teaching calculus, I really appreciate being really comfortable with being able to graph things. It makes calculus so much easier. 20. The limit as x heads to infinity of 3x squared minus 4x plus 4 over x squared minus 4. Now remember, I need you to show, not just say, hey, there's a horizontal asymptote at y equals 3, because I'm looking and I'm seeing the degrees are the same, and so I look at the ratio of leading coefficients. We can't do that on this test. This is a calculus test. Show using the limit. 3x squared minus 4x plus 4 over x squared minus 4. So I'm going to multiply by 1 over x squared on top and bottom, and now that's going to give me the limit as x heads to infinity of 3 minus 4 over x plus 4 over x squared over x squared divided by x squared is 1 minus 4 over x squared. Now when we plug our infinities into these places, 4 over infinity is 0. So I get 3 minus 0 plus 0 over 1 minus 0, and so 3. This limit is 3. Okay, 21 asks me to find the average rate of change. And the average rate of change for f of x, which is sine x plus 1, on the interval from 0 to pi over 2. Wow, that's interesting formatting it printed. That's very uncomfortable. Okay, so average rate of change is going to be f of pi over 2 minus f of 0 over pi over 2 minus 0. So f of pi over 2, I plug a pi over 2 in. F of 0 means I plug a 0 in, and pi over 2 on the bottom. So 1 over pi over 2, when I flip and multiply, becomes 2 over pi, is the average rate of change in f on 0 to pi over 2. Excellent. Okay, what's next? 22. Ooh, there's only 23 problems. We're almost done. 22. Find the slope of the curve y equals x squared minus x minus 2 at x equals a. Okay, so f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. So that's going to be the limit as x approaches a. F of x is this stuff, x squared minus x minus 2 minus f of a. Well, f of a means I plug a's into those. So I have a squared minus a minus 2 all over x minus a. Well, so then we're going to have f prime of a is the limit as x approaches a of x squared minus x minus 2 minus a squared plus a plus 2 over x minus a. And I see the 2's cancel. Does that help? Is everything good now? All right, let's keep going. So now I've got f prime of a is going to be the limit as x approaches a of x squared minus x minus a squared plus a over x minus a. And if I plug in a for all the x's, I got 0 on the bottom and I get 0 on the top. So I still have 0 over 0. I'm not done yet. But I do notice that I have 4 terms here. And I'm wondering what happens if I try and do factoring by grouping. The limit as x approaches a of x squared minus a squared minus x plus a over x minus a. And so now I think, hey, how about the limit as x approaches a of x minus a, x plus a minus x minus a over x minus a. Now notice we can GCF factor out an x minus a from the top. Wow, this is intense. Thinking about going back and doing it with one of the other limit definitions of the derivative. F prime of a then is going to be x minus a, that's the GCF, x plus a minus 1 over x minus a. Oops, don't lose the limit as x approaches a. So these cancel. And now finally, we have x plus a minus 1, and we can replace all the x's with a's, and so I've got 2a minus 1. Wow, that was intense. Okay, so I'm definitely going to go back and use a different limit definition of the derivative. So f prime of x is going to be the limit as h heads to 0 of x plus h squared minus x plus h minus 2 minus all of f of x over h. So f prime of x is going to be the limit as h heads to 0 of x squared plus 2x plus h squared minus x minus h minus 2 minus x squared plus x plus 2. So where did my x squared go? I guess I didn't write it. So that's going to be, what? No. That's f of x plus h minus x squared plus x plus h all over h. Well, what cancels here? I've got a lot of stuff. The x squareds cancel, the negative x and the positive x cancels, and the negative 2 and positive 2 cancels. So now I've got f prime of x equals the limit as h heads to 0 of 2xh, no, yes, yes, there's an h there, plus h squared minus h over h. And I've definitely run out of room, and this line is bleeding into this line, so let's just move away from all that mess and come back here and say f prime of x equals the limit as h heads to 0 of h 2x plus h minus 1 all over h. And now I can finally plug a 0 in for h to get f prime of x equals 2x minus 1. And we want f prime of a, so that's 2a minus 1. Same. And that seemed a little less intense than that other limit definition of the derivative. Okay, well, let's take a look at the last problem then on this review worksheet. It says f of x equals the equation x to the second minus 3x. Find the slope of the curve at the point f of 1. Well, that's going to be 1 squared minus 3 times 1, or negative 2. So the point is 1, negative 2. Find the slope at that point, then write the tangent line, then write the normal line. Okay, so f prime of x is going to be, I could just do f prime of 1 equals the limit as x approaches 1 of f of x minus f of 1 over x minus 1. So f prime of 1 is going to be the limit as x approaches 1 of x minus, because that's a plus, x minus 2, x minus 1 over x minus 1. These cancel. Now I can plug my 1 in, and I get 1 minus 2, or negative 1. So I know f prime of 1 is negative 1. I have a slope, I have a point, I can write the tangent line. Tangent line is y minus minus 2. It's just not enough space for that. Okay. Tangent line y minus a negative 2 equals negative 1 x minus 1. And the normal line is perpendicular, so y plus 2 equals opposite reciprocal x minus 1. All right, so that was the review worksheet. I hope you're feeling confident with all this stuff. Please let me know if there's anything I can help with before you take your test. Take care, everyone.